Let's take a look at an example. We're back to building our similarity formula. So suppose that we have a big collection of documents. We have two documents in this collection. D1 has the word angry and the word aardvark. D2 doesn't have the word angry, but it has the word aardvark twice. And then there's a bunch of other documents in the collection. But we're only concerned with D1 and D2. A user comes along, and the user's query is angry aardvark. Right? Now, if you were that user, would you prefer document D1 or document D2 to be returned? Which document would you guess is more relevant? D1, right? It contains both of the terms that you had in the query. Now, using the formula that we had on the previous slide, which document would get ranked higher? D2. Okay, does everyone see that? Okay. The reason it works out to be that way is in the query we have two words. Both of those words have frequency 1. So term frequency is 1 in both cases. In document 1, you have a term frequency of 1 and a term frequency of 1. In document 2, you have term frequency of 0 for the word angry and term frequency of 2 for the word aardvark. So if we didn't use IDF, the dot product between the query and D1 would have the value of 2, right? It's 1 for the angry and 1 for the aardvark, okay? And again, if we didn't use IDF, the dot product between Q and D2 would have the value of 2, right? It's 0 for angry and 2 for the aardvark. Now, we're taking IDF and we're multiplying IDF by the term frequencies. Now, IDF for the word angry is going to be higher or lower? Lower. Aardvark is a more rare term. It's more content-bearing, so it's going to have a higher IDF weight. So what's going to happen is twice the aardvark is going to have more weight than 1 times the IDF of angry plus 1 times the IDF of aardvark. Because by definition, the second IDF of the aardvark is bigger than the IDF of angry. Right? So what you'll get is a counterintuitive result. It looked like a pretty good similarity function, but it has this unfortunate property that a document that is littered with high IDF words will propagate up to the top if they happen to match the query. Right? So that's not desirable. And how do we correct that? So one way to correct that is to think back to think back to the last lecture. We talked about clumping. We talked about how words are not like lightning strikes, they're like infectious diseases. Right? Once you see an aardvark, if you see an aardvark once in a document, you're much more likely to see aardvarks again and again and again. So if you think about the level of surprise that you as a reader have, you are reading the document, the first time you see an aardvark, it's pretty surprising, right? It's a rare term and you just go, wow. A whole lot of context comes into your mind as soon as you see that word. The second time you see aardvark, what does it do? It basically reinforces in your head that this document is about aardvarks, but it's not nearly as surprising as before. The third time you see it, it's not surprising at all. You're expecting it. Right? It's supposed to occur because this is a document about aardvarks. So the first occurrence of the word is very important. The second is less important. The third is less, and so on and so on and so on. Okay. So we can encode that in our ranking formula by using a squashing function. So we can take the TF, the frequency of aardvark in the document, and squash it. So give a higher contribution to the first occurrence of the word aardvark, a smaller contribution to the second, a smaller to the third, and so on and so forth. There are lots of ways to squash frequencies. You could use a log if you wanted to. A particularly effective way of squashing it is through a formula like that. We take x and divide it by x plus k. So that's a function that looks like that. It asymptotes to 1 at high values of term frequency. And we have this parameter k. Right? It's a meta-parameter, and we can use that meta-parameter to control how aggressive the squashing function is at removing the effect of frequencies. So if we have a large value of k, the squashing function is going to look pretty linear. So every occurrence of the word is going to contribute the same amount, approximately the same amount, to our score between the query and the document. If you have a very small k, it starts approaching a step function. So the first occurrence becomes very, very important, and subsequent occurrences have no importance at all, right? So if you basically, term frequency becomes binary. You either see the word and then you get all of the credit for it, or you don't see it and then you get a 0. Okay, so that's how you correct. That's how you get rid of this unusual behavior where D2 would be ranked higher than D1, because once you squash it, this second aardvark, it's still going to have the high IDF weight, but the effect on the formula is going to be a lot smaller than the first occurrence. Okay. Now, so squashing the frequency is good, but it's not always good. Because frequency, as we mentioned, it's actually quite important in some kinds of documents. Specifically, if you have very long documents, if you have encyclopedia articles, or if you have Wikipedia pages, then frequency is important, because a word that occurs once could be there by chance, and the fact that you see it multiple times actually reinforces the importance of the word in a document. So one way to take that into account is to make our k, the squashing factor and the squashing function, make it depend on the length of the document. So what we'd like to do is, we'd like for long documents, we want to have a large value of k, because we would like the function to grow steadily each time we see the word. We would like to add the same amount to the score. And if we have a very short document, then repetitions are not particularly important, right? So if somebody tweeted, the word aardvark 5 times, or as many times as it fits into the tweet, versus a tweet that contains the word aardvark once, there's no difference. So we want to treat those the same, but a Wikipedia page that has 100 aardvarks should get a higher weight than a Wikipedia page that has just 1 occurrence of aardvark. So the way to do that is we make that k dynamic, right? And what we do is we take the document length, the length of the document that we're trying to rank, and we look at how does it compare to the average document length in our collection. If it's much longer than the average, this is going to be a big number, and we have a smooth squashing function. If the document is short compared to the average, it'll approach a step-like function where it's basically 0 or 1, and it doesn't matter how many times the word occurs. Note that I've still kept the parameter k in there, and that is useful for tuning purposes, right? So different sets of documents usually want a different value of k, and by playing around with k, you can sometimes get your ranking performance to be better or worse.